Hello everyone, this is Spencer Snowling from Hydromantis, and I'd like to welcome you to today's webinar on one of the continuing series that we've been doing now for well over 3 years. Usually once a month we cover a different topic about models in GPSX or one of our other pieces of software. And today we're going to be talking about biofilm modeling. It stretches across a number of different unit process objects, and I'm going to sort of discuss the underlying model, how the different unit processes differ from each other, and then do a couple of quick demonstrations and try to basically in a short period of time describe what we do, how it works, and what are the key things that you need to know when you're setting up a model. So my name is Spencer Snowling. I'm Vice President of Business and Product Development here at Hydromantis, and as you may know, I've been the caretaker of GPSX for most of my career here, actually, to be honest. And so my plan for today is to go through a little bit of the biofilm model details. First of all, just to give you an idea of how the structure works and some of the equations that we're using to describe the behavior of the model. And then I'm going to run through most of the common configurations for our biofilm models and show you what the important parameters are. So basically how to set up the IFAS model, the trickling filter model, the denitrification filter model, and then I'm going to mention briefly some of the other ones as well. During that time, I'll probably pop back and forth a fair bit between my slides and my desktop just to illustrate a few things as we go along, a few final thoughts, and then as usual, I will answer any questions that you have at the end of the webinar. So in your go-to webinar dashboard, there's a spot where you can enter in questions, and I invite you to do so at any point along while I'm chatting away here. What I'll do usually is have you enter those as we go along, and then I'll come to the end of the webinar and I'll take some time to answer those questions at the end. Okay, so in GPSX we have a biofilm model that's used across a number of different types of objects. Essentially that's a one-dimensional flux model with 5 biofilm layers and 1 liquid layer. So in different objects, different unit processes, this is kind of configured in different ways, but essentially it's more or less the same approach across all of the different units that have biofilm in them. So you have 5 biofilm layers, and then each one of those biofilm layers is modeled as an individual reactor. And by that I mean that we have a complete biological activated sludge model running and solved for each one of those layers, and we are predicting the concentrations of all of those state variables in GPSX, like phosphorus and ammonia and all the different forms of COD and oxygen and so on. We are solving for the concentrations in each one of those biofilm layers. So way back when, in version 2.something, 2.2 I think, the trickling filter model was the first biofilm model in GPSX, and we've extended it to the number of other unit processes around the software, and we deal with the liquid configuration and the way that we calculate the biofilm surface differently in each one of these different objects. So you can of course find all of our biofilm type processes under the attached growth processes panel in our unit process table that you find next to the drawing board. So you can see we have a number of different ones that are available there, but they kind of basically break down into the following units. There's the hybrid object. This is probably our most popular model for using for modeling biofilm. And in that case, this is what we use for doing IFAS modeling or MBBR modeling. This is any time that you would have some sort of media in with the mixed liquor. So it can be fixed media, it can be floating media. You can use the hybrid object to do that. We also have 2 different types of rotating contactors. The submerged contactor is, as shown here in the unit process icon, completely submerged, and there's bubbles there to indicate that it is, of course, aerated from some sort of diffuse system. And then we have a rotating contactor that comes up out of the water, your conventional RBC systems, and you specify some details to show how much of that is exposed to the air. We also have an aerated biofilter, or a BAF unit. In fact, we have 2 different versions of that model. We also have a conventional gravity-driven trickling filter, and then also a denitrification filter. And I'm going to come back and talk about each of these in a bit more detail. But for now, I'd like to start by just describing the general biofilm model that we have in GPSX. And as I mentioned, this is the same across all those different units. However, what I'm showing you here, just for the case, is showing you what the plastic IFAS floating media looks like. So what we do is we start by specifying the amount of surface area for the biofilm in some sort of units that make sense for the technology that's being used. So in this particular case, we asked for how much fill fraction do you have, and what's the specific surface area, and so on. And then we calculate into a total surface area of the medium. And that's treated homogeneously. It's one giant sheet as far as the model is concerned. And then we place our 5 biofilm layers on top of that. And then the liquid layer runs over top of that as well. So as I mentioned, if you look at it from this point of view, we have our media surface, and then we have, if you sort of look at this as a cross-section, 5 reactors kind of stacked up one beside each other. Then we have a bit of an interface with the liquid itself, and then we have the rest of the bulk liquid is there. And we are sort of looking at one giant homogeneous sheet of media, and then biofilm and liquid and so on, for each one of these unit processes. And it's within each of these 5 reactors, and as well as the liquid layer out here, that we actually do the calculation of the derivatives for all of the state variables that we have, and then we calculate all their concentrations, and then the composite variables, such as total COD from there. So there's a lot going on in this model. In addition to things like your conventional aeration that you would have in your biological reactions and your physical chemical processes that are part of the biological models that we have in GPSX, we also have a few other things, and in fact 4 other processes that are specific to the biofilm process. One of them is diffusion. So of course, as the soluble components in the liquid to come up against the biofilm, we can have the diffusion of those soluble components, such as oxygen and ammonia, into that biofilm. We have attachment, meaning stuff that's in the liquid gets attached, solids get attached onto the surface. Then we have a detachment of that, of course, as well. And we have the internal exchange of the solids within those biofilm layers. This is all on top of those regular biological reactions that are going on in there, too. So I'm going to run through that in a little bit more intuitive way by showing you this diagram that has some arrows here to sort of indicate all of the processes that are going on simultaneously. One, of course, is the solids attachment and detachment. That's dependent upon the concentrations in the biofilm and in the liquid, and I'll show you the equation for that in a minute. We also have the soluble diffusion. That's in and out of the biofilm. These are, as you can see, both of these processes kind of go both directions. And then we also have our internal layer-to-layer diffusion. So of course, if you have a very large concentration in the outside here, that will start to diffuse in. And then, of course, the solids exchange. And this is there to help drive the growth of the biomass, to allow the biomass to grow. And then as they die off and so on, you get some inert material. It kind of exchanges its way out to the edge here, and it comes off as part of the detachment. We don't do detachment as a discrete event. It's sort of a continuous process. So unlike what you might see in a real biofilm system, we kind of had solids coming off sort of continuously all the time. So to discuss briefly how these equations work so that you can see the way that we've modeled these things. First of all, the diffusion itself is sort of fairly typical. We have a mass transfer coefficient, and then we have some sort of driving force or some sort of gradient of concentration. So in this case, when we're coming from the liquid into that first biofilm layer, we take the difference between the soluble concentration in the liquid and that in that first biofilm layer times that diffusion coefficient, or pardon me, that mass transfer coefficient, and then we calculate sort of a mass over time, how much is going into that biofilm. We calculate the mass transfer coefficient from these diffusion constants that are found for water, and then we multiply that by a biofilm reduction factor. And those are all parameters that are available for you to adjust as part of the calibration process here in the mass transport menu of your object, of your unit process objects. And when we go to the inside, once we're talking about the diffusion from one layer to the next on the inside of the model, pardon me, in the inside of the biofilm, it's basically the same thing, except we're doing it over 3 layers here. So it's sort of finite difference method here. You're looking at, for the diffusion into layer n, we're looking at the concentrations in n-1 and n+1 and n, dividing it. And again, we're applying those same types of coefficients that we use, and that controls how fast that happens. The internal solids exchange is basically exactly the same thing, except, of course, it's done on the solids only, whereas the diffusion, of course, is only on the soluble components. This is only done on the solids, and but we have a solids exchange rate here parameter that's available for you to adjust as part of that mass transport menu, and this is a number that we have internally calibrated from our experience with these models. The attachment and detachment rates are also found in this same menu here, and you can find them here. These numbers don't generally have to be adjusted very often, I find, as long as you have the correct biofilm thickness and the correct surface area. These are first order rates here. The amount of attachment is basically the proportional to the amount that's out there in the liquid. And the detachment kind of works the same way, except that we have this big term here on the end that looks at the maximum biofilm thickness, and it looks at the current thickness. And as these two things, as the thickness increases and that biofilm is growing out to the amount that out to that maximum biofilm thickness, this number on the bottom of the equation becomes very small, and what it does is it kind of ramps up that detachment rate. And it allows you to sort of keep the biofilm growing, and it starts to detach more as it gets thicker. It keeps it from growing past the maximum biofilm thickness value. So what we're actually seeing here is basically a first order rate, except that it can get turned up a little higher when we get out to the maximum biofilm thickness. This allows us to come to an equilibrium that is proportional to the amount of growth happening, but it doesn't go beyond the maximum biofilm thickness that you've specified. Oh, one last point here I should mention is that we have an anoxic shear reduction factor, and this is something that we multiply the detachment by in areas where we have no aeration going on. The idea being that your detachment would theoretically be a little bit less in places where you don't have quite as much vigorous activity with the media banging into each other and so on. Now, we have this set to 1 by default, so it's not actually doing anything until you set in there to actually change that. Okay, so how do we then get to that maximum biofilm thickness? And it's very straightforward calculation for us to be able to take, as I was showing you before, the concentrations that we have for each of these layers, all of those concentrations of the biomass and the particulate substrate and anything else, the inert material that's all going on in there, that gives us a total mass of solids that is in each one of these reactors. We then divide by some of the parameters that you'll see in your menu, things like the dry solids content and the density and so on, and that will allow us to convert from a concentration into a thickness. And so you can adjust those parameters a little bit if you like, but they tend to work very well as they stand. So we take a look at these concentrations and we calculate what a thickness would be from that. Okay, so that's a fair bit of detail that's going on in there. If you ever need to go back and look at how all that stuff works in more detail, you can find that in the GPSX technical reference. There's a whole section there about how we do the attached growth model. So if you ever have any questions, please feel free to email me about how those equations work. What I want to do now is concentrate a little bit on how you get out the information that you want to get out of these models. So first of all, there is a lot of output to manage. If you can imagine, we have for all the different reactors in your IFAS system or all the layers in your trickling filter, you have a concentration for each one of those layers, but also for each of the individual biofilm layers too. So you have a lot of profiles that you could look at and so on. And what you can do is you can plot concentration profiles either through the length of the reactor or through the depth of the biofilm. And those are all things that are available to you to be able to play around with. If you right-click on the object and go to the Output Variables menu, you'll see different types of output variables that are available for you to plot. And these are the ones that you should be looking at, and in addition to, of course, what the effluent quality looks like from the liquid as it's leaving. If you want to look at what's going on inside the actual biofilm, these are the menus that you'll want to come to. So first of all, in a lot of cases, you're going to find the first menu that you could jump to is something that's specific for that particular object. So I'm showing you trickling filter here for the moment. You'll see that there's obviously some trickling filter variables. Those are specific for that unit. But in most cases, you'll have some sort of biofilm profile that you can plot. And this is going to come out as a 1D, excuse me, a 1D vector of concentrations through the biofilm. So if you had, for example, an IFAS system, let's pick an MBBR system, for example, and you had, say, a plug flow type of system, or maybe a couple of tanks in series, and you had some media in those. You want to be able to plot the concentrations through the length of all of those reactors. That's where this is the menu that you could do here. You can come here and see what is my dissolved oxygen, for example, in the biofilm in the first reactor. I could plot that. I could plot that profile through the biofilm in the second reactor as well. Each one of those will be for each reactor. This is sort of going the other way. This is now taking the liquid concentration through the length of the reactor. So it takes all of those liquid concentrations in the reactors in series and plots them. This is basically analogous to the type of profiles that you would plot from a regular plug tank. And then lastly, a 2D array is actually the one where you combine these two things together. They're basically a 2D array of concentrations through all of the biofilm and the liquid layers for all of your reactors in series. So that's kind of the most useful thing. And I have to admit, when I'm doing a lot of biofilm modeling, it's these types of graphs that I use the most to be able to understand exactly what's going on. So just quickly to show you what that looks like, if we're taking a biofilm profile here, this is looking at the biofilm of the concentration profile of oxygen through a biofilm. I think this was from an IFAS system. And we can see here, liquid layer is always the first one, and then number 6 labeled across the bottom, this is the side that's the media. So when you plot these profiles, the liquid will always be on the left, and the media will always be on the right, and then you can see how that goes. Now, when you're plotting the liquid film concentrations, it's of course going from left to right, goes from upstream to downstream. So as you proceed through your system, if they're tanks in series, or say it's a trickling filter, the left would be the top where it comes in, and then the bottom would be the out on the right where it goes out, so on. So you can plot that profile there as well. But it's these 2D arrays that I find to be, as I say, the most useful, where you can see these things together. So I'm going to, pardon me, and then what you want to do is plot these on a 3D bar graph. We've made that bar graph type available specific to be able to plot these particular types of variables. Okay, so just to explain what you're looking at here, the reactors go along this axis and the biofilm layers go along this axis. So the reactors here, this is actually a trickling filter example that I'm showing you at the moment. So this is flow coming in. This is the top of the reactor on this side. And then as we go through the depth of that trickling filter and exit out the bottom, this is the bottom on this side. So we go through those layers in order. And then we have the biofilm layers here. So the ones that are in the front here, this is the liquid layer concentration here. What we're looking at is heterotrophs at this point, the concentration of heterotrophs. So of course it's very low in the liquid, but very high in the biofilm. And our biofilm concentration, we can see here, this very first row is the one that's sort of in contact with the water. And then it's the ones at the back that are the ones in contact with the media, and these are all the other ones in between. So try to, if you want to plot one of these 2D graphs, you put it on there and you pop it up with one of these 3D graph types. You can always remember that the liquid's in the front and the media is in the back, and it goes from left to right as you go through the process of your system. These buttons down here, as I'll show you in a moment, are there to kind of help you to be able to resolve the image here. You can rotate it around, you can make it taller or shorter depending on how much you want to be able to see in terms of the bars that come in behind and so on. Just basically there to help you out. Okay, so what I'm going to do is I'm going to run through some of the details that are specific to the hybrid object first, and then show you a quick demonstration. Then I'll come back and I'll talk about the trickling filter afterwards. So when you're setting up the hybrid model, as I mentioned, it's the same biofilm model that's in all of the other types, except that it's been configured hydraulically for basically a plug flow tank. It's essentially the same model in terms of the way that it's set up for its aeration and for the internal recycles and so on, as you would have for a plug flow bioreactor. And then you are asked to enter in the media fill fraction and the physical properties of that media and so on, and that's how we calculate our biofilm surface area. Now, as I mentioned earlier when I was going through where those equations are, most of those parameters that you're playing around with can be left at the default values most of the time. I haven't found that you have to do a lot of tweaking of variables for the parameters that we have in our biofilm models. You do have to change some of the configuration ones, though, in the physical menu, such as the specific surface area is a real obvious one. If you have one vendor's type of media, they might have a bigger specific surface area than another type. We have, I think, 500 meters squared per meter cubed as our default. You may find that you have to change that higher or lower. Of course, that's going to have a very significant effect on the amount of surface area that we are calculating overall for our model, so it's an important parameter to get correct. And then some parameters can be adjusted during the calibration to calibrate the model to the observed performance, and those typically are the maximum biofilm thickness is one of the key ones in order to be able to make sure that you get the right amount of biomass on your biofilm. So these things are all found in the physical menu. The reactor portion filled by the media, you can have a different value in each of the tanks and series that you have if you like. These media ones, there's the specific surface area of the media that I mentioned earlier. This is an important parameter. Make sure you have correct for the media that you're modeling. And there's that maximum biofilm thickness that I mentioned as well. The other mass transport menu that I mentioned earlier, this is where you find the things like the attachment rate and the detachment rate and the reduction in biofilm and so on. For the most part, I generally don't always have to come and change these. I tend to leave them alone unless I'm really suffering with my calibration. I can't make it match. Then I might come in here and see if I need to adjust some of these parameters. Well, as always with all the models, your influent characterization is important. So, of course, you are, the concentrations that are going to be predicted by this model in the biofilm layers are quite high. You're going to be growing a lot of bugs. You're going to be having a lot of cell death and producing a lot of inert material. If you have a lot of inerts in your influent, of course, they're going to get sucked up into the biofilm, at least some of them, so it can have a big effect on your model. Maximum biofilm thickness, as I mentioned, can be quite important. And as I suggested, try to plot those biofilm profiles to try and understand what's going on when you're going through your model calibration process. Okay, so let's take a quick look at that now. All right. So this is GPSX. I'm sure most of you are probably familiar with what it looks like, but just in case you haven't seen it before, we have this drawing board here, and we have the unit processes. Here's the suspended growth ones, and here's the attached growth ones that I mentioned, and here's the hybrid object that we were discussing earlier. So what I want to do actually is open up the sample layout that we have that's available for you to use when you install GPSX on your computer. All of these pre-configured models will come available to you. So I'm going to go down here to this MBBR IFAS system. And you can see here I'm gonna go back to modeling mode here so we can open up one of these menus nicely. If we go here to this physical menu, as I mentioned, this reactor portion filled by the media is something that's quite key. Might be 0.4, 0.5, 0.6. We use by definition a 50% fill here. It of course is going to be directly impact the amount of surface area you have for your biofilm. And these are the other items that I mentioned before. I'll note here in the operational menu, this looks pretty much exactly the same as you have for the plug flow tank object. You can specify airflow and turn DO controllers on and so on, except that you'll notice down here where you specify your internal recycle, you can actually specify whether that internal recycle contains the media or not. If you have different concentrations of media in your tank, for example, in certain parts and lower concentrations in other parts, that might be relevant to your system. Okay, so I'm just going to run this here, get a steady state solution. And we can see when you double click on the quick display panel here, we can get some obviously process here. This is fully nitrifying plant. The operational variables that you'll see here do include some things that are specifically about the media that's being used. But the one thing I want to do is take just a quick look at these profiles that we have here. These are some of the ones that I mentioned that you could take a look at. So we can see here for tank 1, the first of the tanks that this goes through, we can show our DO profile and so on. So this is the kind of information that's available, and this is how you set up the MBBR or IFAS. Of course, it depends on whether you have a recycle or not, whether it's MBBR or IFAS. Okay, so I'm going to come back here to the slides and briefly discuss setting up the trickling filter and the denitrification filters. These are, again, slightly different, again, using that same biofilm model, but in a different kind of hydraulic context here. Now, unlike previously where we had some media that was floating around in a large amount of liquid volume, in this case, these are packed beds with some sort of void space in them. The trickling filter model, we assume in that void space that there is water flowing through there, and also that there is some air space in there as well, obviously to allow for aeration of that of the liquid and then subsequently the biofilm. Excuse me. And then the denitrification filter is different, though. Generally, bottom loaded. Sometimes we have both bottom loaded and top loaded, but bottom loaded, and it's a fully flooded filter, so there is only water. There is no void space of air in the denitrification filter. So the key to setting these ones up is to define the media surface area correctly and also the HRT of these particular systems. In addition to that, the denitrification filter also has a solids capture, because what we did was we wanted to be able to capture the performance of the filtration going on, but without going into extremely large amounts of details of trying to model the filtration in a dynamic sense. So you specify a solids capture and a backwashing rate, and then we figure out how much solids come out of that system and put that out through the backwashing connection point on that object. And then basically all the other parameters in terms of the biofilm are the same as what I previously showed you for the hybrid. So the key things looking at the trickling filter is to, first of all, specify the filter surface area and the depth. That is, of course, the entire system that you have, the top surface area. And then you specify that specific surface area of that media. So we take the total volume and then multiply by this number to get to the specific surface. We, of course, also have the liquid retention time in the filter. Now, this is different than actually all of the other types of models that we have. As you probably know, if you're modeling conventional activated sludge or most of our other objects, HRT is actually something we calculate. We don't normally ask for that. So in this case, it's different because it's difficult for us to ask you, okay, how much liquid is there in your trickling filter? Because it is somewhat unusual in the sense that you have that void space that's partly filled by liquid and partly filled by air, and that's not a number that most people who use our software will know. So it's more likely that you would know actually what is the residence time of the liquid going through my trickling filter, and from that we can calculate everything else that we need to know. If you find that this is not a constant value in your particular system, I can show you how they can make this vary with flow. So for the denitrification filter, that's not a problem because we know that all of the area that's not media is filled up by water. So we can calculate that, and again, you specify the filter properties in terms of its surface area and depth. And then we have that specific surface area of the media again, but now we ask you for the porosity, and we can figure out how much water is left over after that. So just very quickly to show you what that looks like, we have a trickling filter example in those sample layouts menus here. And so I'm just going to very quickly run a simulation here. And we can see, looking again the biofilm profiles. Here's an example, by the way, of one of those 2D graphs. And this is again looking at the flow coming in from this side and then progressing through the depth of the filter and leaving through the bottom. And this is the liquid layer in the front and the media at the back there. This is autotrophs that we're looking at in this concentration. And we can see the same thing here for soluble substrate, for example. So there's lots high concentrations coming in the beginning, and a lot of that is diffusing into that biofilm, as you can see. But by the time we go through the depth of that whole trickling filter, it's been quite thoroughly used up. And it's kind of an interesting profile to look at it in this manner so that you can see how it changes through the depth and into the biofilm layers. And as with all of our other graphs, by the way, you can click on any one of these bars to find out what that value is. And we can see here something like this, ammonia that's diffusing all the way through, and it's being nitrified as it goes through the length of that system. And we can see our DO and so on, an example. This is a nice way to be able to sort of intuitively understand what's happening in that biofilm as we go. And being that I'm running a little bit long, I won't dwell on the trickling filter, pardon me, the denitrification filter, other than to mention that you can find an example of it here. The fourth one down from the top with the nitrifying plant with a denitrifying filter on the end. Okay, back to the slide here. I'll just mention these other biofilm models as well. The rotating contactors, the RBCs and the submerged biological contactors are both there for you to use. They're different objects. The RBC, you specify some details about the specific surface area on the disk and how much area you're working with, and then the percentage that is exposed to the atmosphere at any time, and figuring out what percentage of that is submerged. The SBC is, of course, different. It's fully submerged, and it has a full diffused aeration model, just as you would find in a completely mixed reactor, and you can specify airflow rate and oxygen transfer efficiency and so on. So just to point out here, these two models essentially work kind of the same way. You can have tanks in series, and you can specify a lot of the details here. But the key thing to put in the RBC is that submerged fraction of the biofilm, which we have it set at 40% by default. And lastly, looking at the BAF models. And I debated about leaving BAF out of today's webinar, and in fact I sort of have. I just have one slide to talk about them today. They are a fairly complex system, and I could probably do a webinar just on BAF models by itself and last for 30 minutes. So I may do that again in the future. But just to mention that we have two objects that you'll find, the simple BAF model and the advanced BAF model. The simple BAF model is actually new. It's new in version 6.3. Basically, you specify the media properties and the size of the reactor and so on, the solids capture, and also the airflow being supplied to that system. And it predicts effluent quality and sludge production and so on, just like you would get from the IFAS model. And it also solves very nicely for steady state. The advanced BAF model, basically you specify all of that, plus there's quite a lot of detail there about the operation. How many units do you have in service at any time? How many are being backwashed? And how many are in filter mode and so on. And they have different things for taking service, things on and offline as it rotates around. It also predicts things like the actual dynamic removal of the solids and how much head loss do we have as that filter fills up and so on. Because of all of that, it's not really a steady state system. There's always something turning on and off or backwashing starting and so on. And therefore, you can't solve it for steady state. You have to run a dynamic simulation for a period of time to be able to come to some sort of convergence of an answer. It is quite complicated to set up. I'll be frankly honest, it's actually the most complicated thing that we have in GPSX, is the advanced BAF model. And I had worked on a couple of projects recently where I didn't need all of that detail. I just wanted to get the right amount of surface area with the right amount of aeration and so on. And so we created the simple BAF model to be able to do that job. So if you're new to BAF modeling, I suggest sticking with the simple one to start. So I'll just very quickly show you that BAF model that's available. Again, back to the sample layouts menu, down to simple biological aerated filter. And here it is, this particular unit we have top loaded. No, I'm sorry, these are all bottom loaded. And I'm just going to run a simulation here and let that converge. And once that comes to an answer, we can take a look at these. There we go. We can take a look at these 2D plots here. And again, what we're looking at is as we go through the filter, it's loaded from the left and goes through and exits out to the right, and the liquid's in the front and the media is in the back. And in this particular case, we're using our comprehensive library. So this is two-step nitrification. We can see the ammonia going down the depth of that bath unit. At the front end, of course, there's more ammonia being converted to nitrite, so more nitrite in the middle of the length of that, and then, of course, nitrate at the end as we get all the way through. And if we look at our biomass concentrations, which I believe I have, yes, okay, so that's correct. So the liquid is in the front and the media is in the back, going through it as we go from left to right. You can see there's lots of heterotrophs available here, and then there's AOBs and NOBs that are doing their job. The AOBs are kind of in the middle, and the NOBs are somewhat towards the end. And we can look at how that population distribution changes with different parameters such as the loading and the temperature and so on. And so this is doing its full step denitrification. And we have also got some PAOs in here, some BioP bugs, which I don't think are actually doing BioP. I think really they're denitrifying along with the regular heterotrophs. Okay, so let me pop back to my slides again. And there we go. So a few final thoughts. The key thing with any biofilm modeling that you do in GPSX is to get the surface area of your media and the biofilm thickness right. That is essentially the thing that defines how much biomass that you have in your system, and that, of course, is what you're trying to calibrate and what you're trying to predict with your model. It does require these biofilm models. There's more to them. They have to require some extra calibration compared to what you would do for just a regular conventional activated sludge. And they are computationally more intensive. You have essentially 6 times as many concentrations that you have to solve for, because now you have 6 biofilm layers instead of just 1 tank. It is complex, but it's actually quite robust model. We've had a lot of success with it. It's been in GPSX for almost 15 years now. It's a mature model, and we feel very confident in using it. And we do use it quite regularly in our own consulting business. Okay. So I'd just like to have a few words here at the end, and then I'll hang around and answer some questions. I see that we've got a few questions here. If you have any right now, if you have any that have come to mind, type them in there, and I'll get to them in one moment. Just like to mention that, of course, as usual, Hydromantis will be at the WEFTEC conference in New Orleans very shortly, coming up in about a month. And we are at booth 2839. If you are attending WEFTEC, I would invite you to come by and say hi. If I haven't had a chance to meet you in person before, we will be demonstrating the new version of GPSX, version 6.4, that will be coming out later this fall. We also have demonstrations of Toxchem, our air emission software, and also we'll be previewing a little bit of a sneak peek of CapNetWorks. We're having a new version of CapNetWorks come out this fall as well. At any time, if you miss any one of our webinars, you can hop over to our YouTube channel, which is youtube.com/Hydromantis. And in our playlist there, we have recordings of all the webinars that we do. If you've missed any of the ones that we've done recently on our sludge disintegration modeling, for example, or the aeration or the clarifiers, which is the one that I did last month, you can always come here and take a look at that webinar after the fact. We offer online training workshops. This has become actually our quite popular, or probably our most common way to deliver training. It's via the same type of technology that we're using to do the webinar right now. We can offer that for Toxchem and GPSX, usually a 2 or a 1-day seminar. We released the new version of Toxchem, version 4.3, a couple of months back. You can come to our website and find out more details about it. And I'd like to let you know that in September, on Tuesday, September 16th at 2 p.m. in the afternoon, we will be doing the next webinar. It will be our relatively popular Back to Basics. Quite frequently, I get requests for people to say, can you just show me how to set up a model? So we're going to go back and we'll just talk about the basics of setting up a model, talk about what's important. What are the key things that you have to know when you set up a model in GPSX? So we'll show you a little bit of the interface. We'll show you the key things that you need to know about modeling a conventional activated sludge system. Sorry I don't have the registration link up on our website right now at this moment, but I'll have it before the end of the day today. Keep an eye on your email, and we will be sending around an invitation there as well. And at any time, if you have a suggestion for a webinar topic, if there's some aspect of GPSX or any of our software that you are interested in, please feel free to email me or the webinars@hydromantis.com address with a suggestion for our webinars.